So, welcome everyone to today's seminar. Today we have Ángeles Pérez Villegas from the Instituto de Astronomía at UNAM in Mexico City. She's going to talk about globular clusters as tracers of dynamical and chemical evolution of the Milky Way. Actually, she is from the UNAM at Ensenada, Mexico, and I started reading the other way around. So she got her PhD at UNAM, Mexico City. Then she moved to Morelia, and then she held postdoc positions at the Max Planck Institute in Garching, and then at IAG in USP here in Brazil. And thank you so much for accepting our invitation. The floor is yours when you're ready.
Thank you very much, Anna. So for me, it's a pleasure to be here. Actually, because when I was in Brazil, I didn't have the opportunity to go to Porto Alegre. And now for me, it's a pleasure to give this talk, in particular because all the work that I did about globular cluster was when I arrived to Brazil with Beatriz Barbuy. That was amazing for me, that experience. And now I want to tell you all the work that we have been done in this topic because they are really, really excited. Well, let's start. First, I will to start with a small introduction about the globular clusters. Well, in particular, the globular clusters are the most ancient stellar system that we have in the Milky Way. And this is, in particular, it's very interesting that the stellar distribution that the globular cluster has is like spheroidal, mainly, even in the cases, we can have some cases where these are more elongated, but we could say that is probably spherical. And since we have information of the Milky Way globular cluster, first from Harris 2010, we know that there are 157 globular clusters. But later, with a very nice compilation from BCAF from 2019, we know that now we have 200 globular clusters. And in the following years, also, we have new globular cluster, in particular in the bulge region, plus some candidates. And if we put all this together, now we have a globular cluster plus candidate, 295 objects. That is really interesting because in the past we have a very we have a very concern about the number of globular clusters that we have in the Milky Way if we compare with the M31, in particular because at least the identified globular clusters in the M31 was 360, and if we assume that Milky Way and the M31 are quite similar galaxies, so it was like a worry. But of course, many of globular cluster will be discovered in the following years, even though with the surveys that we already have, like Gaia and VVVX, or the upcoming surveys like LSST. And this is in particular, this is a very nice the information of globular cluster that we have, in particular in the inner part of the galaxy. And this is roughly the boundary of the peanut bulge in the galaxy. But what happened if we look at the metallicity distribution function of the globular clusters? Well, we can identify a very nice two peaks, one like a metal poor metallicity distribution or and a metal rich. And this is interesting if we see what is the distance that are of those globular clusters, and we could see that in particular the metal poor population are more extended in the galaxy. So this histogram of the metal poor population that are metallicity minus less than minus 1.1, we can see that are this blue histogram, and they are going through in the inner part of the galaxy, but also very far away from the galaxy center. But now if we look at the distribution of metal-rich components that are larger than minus 1.1, we can see that these globular clusters are more confined in the inner part of the galaxy, inside like 15 kiloparsecs from the galactic center. But also we can see here interesting peak, like we know that we call those globular clusters that moderate metal poor globular clusters, that the metallicity is roughly -1. And those clusters are very confined in the inner part of the galaxy. I mean, this is like inside 6 kiloparsec, and this is really interesting because these galactic globular clusters are confined in the bulge part, and also we know that this metallicity of this higher metallicity is because of the rapid chemical enrichment that happened at the beginning of the galaxy formation. But why do we study globular cluster? Because in principle, they are some spherical objects, but we can learn a lot of things if we first study the globular cluster like individual objects. For example, they are the perfect laboratory for study stellar evolution. And this is because the stars are, all the stars in the globular cluster has roughly the same age and the same chemical composition, but different masses, where in that case, we can see what is the evolutionary stage of that star. And also, we can identify this characteristic of multiple stellar population that is really, really nice. And actually, we know like most of the globular cluster in the Milky Way has evidence of the multiple stellar population. And that is really interesting because now this is completely different story that we already know about the globular clusters. But also we can use this globular cluster like a system. And that is also really very, very important because they are a fossil record of the dynamical and chemical condition during the galaxy formation. And for example, if we only concentrate in this plot, that is the angular momentum versus the energy, we can identify the different globular cluster population. If we see these blue dots or symbols are the globular clusters that are mainly in the bulge or Barg galaxy, and also the yellow one, or the orange one are the disk. And here the purple, the red, green, and brown are the different accretion events that the galaxy experienced. That's why like an entire system of globular clusters, we can learn what is the story of the galaxy, and that is really, really exciting. But also, if we put all this together with the information from Gaia, in particular the proper motion, that is because for the first time when Gaia arrived and provide a lot of astrometric information, for the first time we have accurate absolute mean proper motion from the non-globular clusters of the Milky Way. And that is really important because in the past we already had information of the proper motion, but they didn't they didn't were homogeneous determination, and also the errors were not so small. And with Gaia, we had a very small error in proper motion in a homogeneous way, and that's and that's why that is the perfect timing for an orbital analysis of the globular cluster in order to understand what happened with the dynamics and the distribution, the spatial distribution of the globular clusters. This is also very nice because even though that the Gaia has a lot of the limitation, but also we can have information for the globular clusters that are associated to the Barr-Bulge region. And if we put all this information together with the, for example, the position of the globular cluster plus the distance, radial velocity, and proper motion, and then we can have the entire 6D phase space vector. And also, if we assume a galactic model, then we can obtain the orbit, and this is all these are the ingredients for an orbital analysis that are perfect. If we also combine ages and chemical information, and now we can construct a history of the galaxy in at least in based on these parameters. Also, that is very important that when we can have errors in so when we can have errors in these observables, it's important to understand that there is not only one orbit for each globular cluster or for each individual star in the galaxy. We have like a sample or orbit, and for example, this is a map where in the blue, the red part is the more dense part when we can see the most dense parts when we can see that the globular cluster is passing through the galaxy. And this is also really, really important to take into account uncertainties because there is not only one orbit for a specific globular cluster of stars. And that's why the chronochemodynamical analysis is a perfect way where we can do this kind of analysis in the galaxy. In terms of if we have a very nice color magnitude diagram, then we can obtain the ages of the globular clusters through isochrone fitting. And this is if we assume, like, for example, a Bayesian approach to obtain the age of the globular cluster is a very nice way to have a more accurate age determination. And we also have information from the high resolution spectroscopy. We can have abundances information with a very nice metallicity determination. And if we have the 6D phase space vector of the globular cluster, then we can construct or estimate the orbital parameters. That the orbital parameters are the perigalactic distance, that are the minimum distance from the galactic center, the apogalactic distance, that are the maximum distance from the galactic center, and the maximum vertical excursion from the galactic plane. And also another important quantity that we can get from the orbital parameter is the centricity. That is the combination between the apogalactic distance and the perigalactic distance. If we also we can have the integrals of motion, that if we are assuming an axisymmetric potential, we can have the conservation of the total energy, the angular momentum, and if the case where we have the bar of the spiral arm structure, then the only integral of motion that we can conserve is the Jacobi energy. And these quantities are important because they can help us to identify the similar nature of the galactic, the stellar populations. If we have these orbital parameters, we can make a classification of the globular clusters. In particular, for example, if we use the apogalactic distance and the maximum vertical excursion, we can identify the different stellar population of the globular clusters, and we can divide them in between bulge, bar, thick disk, inner halo, and outer halo. And that's why this is very important, in particular because, for example, if we see the globular cluster spatial distribution, for example, in the projection XY on XZ, and this is like, for example, the bar in the galaxy where there is the distribution of the bar, we can see that all the globular clusters that are in the inner part, we could think that maybe all these clusters belong to that component, but that is not necessarily true. That's why that's why it's very important to use the orbital parameter information, even though all these clusters that's here, I would say, well, all those clusters belong to the bulge bar component. But in the moment that I identify the estimate the apogalactic distance and the maximum vertical excursion, I can see that that is not completely true. And look, the globular clusters that according with the apogalactic distance and the maximum vertical excursion belong to the bulge bar components are the purple ones. The others globular clusters, that the yellow, the cyan, are contamination from the other galactic component, and that is because the inner part of the galaxy is the most complex region of the galaxy, because all the galactic components overlap in that region. That means that we have bulge contribution, bar contribution, inner halo, and thick disk contribution in that region. And that's why it's very important not only classify the globular cluster based on the current position, but also but using the orbital parameters to make a classification. But also, if we just only consider the age and metallicity, we can make another relation in order to identify the two different groups of the globular cluster. And that's why we use the age metallicity relation, where we can, as you can see, we can have like two branches. This branch that the red, we can fit a red curve, or at the blue one, we can identify the different nature of the globular cluster, in particular the ex situ or in situ. That means that because the galaxy have experienced a lot of accretion events, when the different dwarf galaxy were merged with our galaxy during the galaxy formation at the beginning of the galaxy, well, all these globular clusters that belong to those dwarf galaxy, also they are now in our galaxy and have completely different chemical history. And that's why when we have this plot, we can identify the clusters where form in situ and globular clusters that form in situ. And this is another way that we can identify this or classify the globular clusters. And in particular, for example, this is the Milky Way merger tree, where in this tree, we can see that there are many accretion events. We have Kraken, Sequoia, Sagittarius, Helmstring, and Gaia Enceladus. And all these accretion events also provide or contribute to the globular cluster system of the Milky Way. And here we can see this part, this color bar represent the stellar mass that contribute to the globular cluster, and also the moment where this accretion event happened. Like, for example, if we see that the Kraken contribute with approximately 13 globular cluster, and this accretion event happened roughly 11.5 gigayears ago. And this is like one of the first accretion events that we can identify. And also, yes, the Helmi stream has 5 globular cluster, and in particular, I would like to focus in Gaia Enceladus. Gaia Enceladus was the most recent massive event, and also the contribution of the globular clusters of the globular cluster system with the Gaia Enceladus is 20 globular clusters. And that's why one of the most important accretion event, and that's why I will focus a bit in this structure. But what is Gaia Sausage Enceladus? Well, first, it was detected with Gaia Data Release 2, and this is the remnant of the last major merger of the Milky Way, and it happened like approximately 10 gigayears ago. And how was identified? And first, why is Gaia Sausage Enceladus? Because there were 2 groups where they were working in the similar sample. And for example, Amina Helmi analyzing the kinematics of the stars from the Gaia DR2, she applied the Tombre diagram, that is this plot where we can identify the thin and thick star disk. This is the thin disk, this is the thick disk, and also this is some contribution of the halo stars. And she identified like a bump in this region, in the velocity distribution. And she called this a structure like Gaia Enceladus, because for her it seems like something that is emanation from the galactic disk. And this is based on the Greek god. And that's why for her, this structure is Gaia Enceladus. And on the other, from the other group, Belokurov, now he was analyzing in different metallicity beams and with different vertical position of the stars, and also he identified a bomb. And like this is like, if we are going in the different columns represent the different cuts in metallicity, and the different rows the different position from the galactic plane. And for example, here we are close to the plane, like between 1 to 3 kiloparsec, and this is more metal poor component, and this is more metal rich component. And also we can see like this is like a disk star, but when we are going through a less metal poor population, that means a most metal rich, they found this bump. And also we can see, and that's why for him, it seems like a sausage, and that's why they call Gaia sausage. And actually in the literature, now we know this structure like Gaia Sausage Enceladus. But this is one of the most exciting contribution from Gaia DR2, because it was assumed in the past that in order to have the chemical enrichment that we have in the galaxy, it was needed to have the contribution of some massive accretion event in the past of the galaxy, but it was not observed the star. With Gaia, we were able to observe those stars, and this is the evidence of this accretion event. And also, since these moments, many of the accretion events had been identified in the galaxy. But now we can try to look for the globular cluster that belong to this Gaia sausage Enceladus. And if we use, for example, the Gaia early data release stress, and we combine with the metallicity and chemical information from Apogee data release 17, we can apply different criteria in order to identify a pure Gaia sausage Enceladus sample. And we adopt the criteria from Follett et al. 2020. And in this plot, where is the angular momentum versus one of the action, we can identify here the stars that belong to the Gaia sausage Enceladus. Here is the disk, and here we can see the halo. And also, it's very difficult to identify the stars that belong to the stellar halo and the thick disk, because this is a continuum. So there is it's not a cut or gap between the stellar components, but now we can use different diagnostic in order to identify a most pure sample. And for example, there is another empirical diagnostic where we can identify the accreted stars, like is with these chemical elements, aluminum over iron versus magnesium over magnesium. And in this plot, we can see the blue dots, where are those dots represent the Gaia Enceladus. We can see how, if we compare this small box where we can identify based on the Follett criteria, only using dynamical information, also we have some contamination from in situ stars. And if we combine now with this chemical information, we can isolate better this accreted star and to eliminate those stars that are in the same spatial distribution of the Gaia sausage Enceladus, but all those stars are just contamination. And now, if we look like the azimuthal velocity versus the radial velocity, but this is not the line of sight velocity. This is the component r in cylindrical coordinate. And we can see where, if we put this is r, in this part, we identify the stars that belong to Gaia sausage Enceladus. And in the black dots and the color dots represent the globular clusters. And we can calculate the probability of each globular cluster that in the same region in this velocity distribution, to see if belong or not to the Gaia sausage Enceladus. And using the combination between the velocity distribution plus angular momentum in Z component versus energy, we can identify like a 19 globular cluster with a probability higher than 70% to belong to Gaia sausage Enceladus. Well, as we first see that we can identify also these clusters in the H metallicity relation, now we can select all these clusters and to put in the Gaia, in the H metallicity relation in order to see if are consistent with the accreted component. This is a tricky part because the uncertainty of the age determination is sometimes big. That's why it's very important to have a homogeneous age determination. And that's why when we took all the globular clusters that we had photometry information from Gaia, and we estimate the ages, assuming a Bayesian approach, and with combining with the metallicity from Apogee, we identify also that all these globular clusters that we identify in kinematics and dynamics information based on that belong to the gaseous enceladus, and now in the edge metallicity also those clusters belong to this accreted component, and now this is also a confirmation where these globular clusters in fact belong to this accreted component, and according with the velocity information and the dynamical information, those clusters came from gaseous enceladus. But also, if we think most of the galaxies, even though the dwarf galaxies, host a nuclear star cluster. And now the question is, what happened with the nuclear star cluster of the gaseous Enceladus? Is already some cluster that we can see in our galaxy, or that cluster already was dissolved because of different mechanisms like dynamical friction or tidal effects. And again, we took our globular clusters samples that are consistent with the to belong to gaseous enceladus, and we see in the velocity distribution and the angular momentum versus energy space, and we identified in particular two candidates. One, Omega Centauri, that if we see the Omega Centauri in this plot, is this star, the red star. And the second is NGC 1851. But that NGC 1551 is this globular cluster, is the red one here, and we can see that is this, the red one. Okay, but how we can identify, because the Omega Centauri is very far away from the bunch of the stars of the gaseous Enceladus, because I forget to mention that the blue stars, sorry, the blue dots are the stars of the gaseous Enceladus, and the dots, the colored dots, are the globular clusters. But also, when we have all those two candidates to be good options, or the nuclear star cluster of the gaseous Enceladus, we can see if, according with the prediction of the mass of the galaxy and the mass of the nuclear star cluster, we see that in fact the Omega Centauri seems to be the most probable cluster that could be a nuclear star cluster of the gaseous Enceladus. But something that is important to take into account here is that the mass that we are assuming in order to see if this is consistent with the mass of the galaxy, so the mass of the globular cluster that here we are assuming is the actual or the current mass of the globular cluster. And that is something that is not entirely correct, because based on different mechanisms, the globular clusters already could lose a lot of mass during the time. But at the moment, this is our best candidate to be the nuclear star cluster, is Omega Centauri. But now we can take as individual globular clusters and to analyze if those are part of the accretion component of those are part of the in situ component. And in particular, for example, here is the case of Palomar 6 and NGC 6355. Those clusters are very interesting because they are in the inner part of the galaxy. Here is, if we see the projection with respect to the galactic center, and Palomar 6 is very, very close to the galactic center, and NGC 6355 are in the boundary of the bar component. And also this is, it was interesting for us to make this analysis in particular with those clusters, because for the Palomar 6, we have a very wide range of distance. We didn't have age determination, and then we estimate for the first time the age of Palomar 6. And NGC 6355, it was not information about the chemical abundances. And that's why we use those clusters like good candidates to analyze. When with the isochrone fitting, we identify like the age of Palomar 6 are very old, 12.5 gigayears, and the distance is 7.67 kiloparsec from the sun. And NGC 6355, the age, it's also very old, 13.2 gigayears, and the distance from the sun is 8.54 kiloparsecs. And now the question, if those clusters are part of the bulge or not, of the bulge bar. Then if we estimate the orbital parameters, and if we use this classification based on the apogalactic distance and maximum vertical excursion, we identify that the Palomar 6 has a 99% to belong to the bulge component. But this is important. This classification based on the maximum vertical excursion and apogalactic distance is the classification today. Is based on the information that the globular cluster has today. That is important, because if we try to identify the progenitors or the classification in terms of component based on other parameters, maybe the classification will be quite different. But that is because the assumptions are not the same. So that is important to consider. And also the NGC 6355, the probability to belong to the bulge, it's also very high, is 95%. This is really, really interesting. And also the excursion that have both clusters are quite similar. But if we see, well, these clusters are in situ or ex situ, then Palomar 6, and if we are considering this diagnostic, the chemical information, Palomar 6 is this magenta star, NGC 6355 is a yellow one. And the background are the stars in the inner part of the galaxy. It's a chemical information from the bulge stars. And we can see that Palomar 6 are perfectly is in the in situ region. There is no doubt that this globular cluster belongs to the in situ component. But if we look at the NGC 6355, well, it's in the boundary of the between in situ and ex situ component, but a very huge error bars in the aluminum over iron. So then, I mean, for me, this is not conclusive to say that NGC 6355 is in situ or ex situ. Also, if we look the angular momentum versus the energy, in order to identify if the globular cluster is accreted or is in situ, well, the answer is not conclusive because we can see like the blue contours belong to the main, for the bulge stars, and we can see that the both clusters belong to, where are in this region, the Palomar 6 and 6355. But if we compare, for example, with the Heracles, that is another accreted component, also we can see that the is not easy to identify because both clusters are in the low energy region with the angular momentum very close to zero. So then that is not easy to identify. We need more information, in particular for the NGC 6355 about the chemical abundances in order to have a better idea where this cluster belong or not to the main to the accreted component or to the in situ component. And if we see now the H metallicity relation, well, we can see that Palomar 6 is close to the in situ component with a error bars that are not so big. But look, the NGC 6355, even though that is exactly passing through the blue line, but the error bars are huge. And also, we need to improve the H determination of this cluster in order to have less uncertainties. Well, now we have better distance information from the entire globular clusters of the Milky Way. We can do again this globular cluster classification based on the orbital parameters, the APO and the maximum vertical excursion, and to identify those clusters, which cluster belong to the bulge bar region, to the thick disk, inner halo, or outer halo. And the thing that we can see in this plot is we can estimate the probability of each cluster to belong to each component. And based on this orbital classification, we identify like 25% of the globular cluster belong to the bulge bar region, 35% of the globular clusters are thick disk, 12% of globular clusters are inner halo, and 28 globular clusters are outer halo. But now, also, if we have this this information, we can only select the globular cluster that belong to each component and to see again the H metallicity relation. And this is also the similar plot as before with the probability to belong to each component. And we can see, like, for example, all the globular clusters that belong to the bulge bar are mainly in the in situ branch. So then most of them, well, we can have a couple of globular clusters that based on the errors could be in the accreted component, but most of them are in the in situ. If we now look the thick disk, we can see like we have globular clusters that are in the inner, in the in situ component, and also we have some clusters that are in the accreted component. Inner halo, most of the globular clusters are in the ex situ component, and a couple of them are in the in the in situ component. But this is also super interesting that in particular, all the clusters that are classified like the outer halo, all of them are classified also or belong to the accreted component. That is really, really interesting. And now with that, with that information, we can see what is the metallicity distribution function of the galactic globular clusters. And we can see, like in the bulge bar component, we have two galactic, two stellar populations, or well, globular cluster population, one population with a metal poor metallicity, and the second with a most metal rich. And the thick disk, we can see like also there is, well, I cannot believe in this peak because we have not enough information in those clusters, but also here we have something that are also metal rich. The inner halo, we have also different peaks in this metallicity distribution. But in the outer halo, it's also very clear that the most of them are very metal poor, but also is something that there are a couple of globular clusters that are in the outer halo that are very metal rich compared with the others. So it's something that we can look in a better way in order to see if these metallicity distribution function are good enough to identify these stellar populations in the globular clusters. Well, I would like to finish that to mention that it's very important to analyze the globular clusters in the entire context, and that in order to do that, it's needed to make a chronochemodynamical analysis. Otherwise, we will have just a part of the story. So it's important to combine the age, the chemistry, and the dynamics. The globular cluster in the Milky Way, we can identify two groups, the in situ and the accreted component. In particular, with the Gaia Sausage Enceladus, we can say that that structure is the structure that had contributed a lot with the globular clusters in the Milky Way. Omega Centauri is a good candidate to be the nuclear star cluster of the Gaia Sausage Enceladus. If we focus in Palomar 6 and NGC 6355, those clusters seems to be consistent with the in situ origin, belong to the bulge component, although in particular 6355 is in the boundary between the in situ and ex situ, so we need more photometric and spectroscopy data in order to have a better age determination and chemistry information. In terms of the metallicity distribution function, we identified that the bulge bar globular clusters show clearly a peak at -1 that is consistent with the fast chemical enrichment in the inner part of the galaxy. And all the globular cluster classified as outer halo belong to the accreted component. So thank you very much.
Thank you, Angela. Very nice talk. We have some questions. Basilio, would you like to come closer?
Okay, it's actually a couple of questions. One, you mentioned that the galaxy now has nearly 300 globular cluster candidates. That's from the start of your talk. I wonder whether these candidates include the very faint clusters found in the halo. They are very metal poor, like the globulars. They are very old, like the globulars, but they are not as rich in stars. They are very faint. I wonder if these faint halo clusters make up these nearly 300 sample? That's my first question. The second is, you seem to have split in the end of your talk, the globular clusters, for which 6D phase space information is available. You split into bulge sample, thick disk sample, inner halo sample, outer halo sample. So fine. I just wonder, and that's based on the Zmax against apogalactic radius. I wonder how these could be affected by uncertainties in the proper motions, and also by the adoption of different galaxy models in the orbital reconstructions. Will they move these clusters significantly from one component to the other? That's my second question.
Okay, so according to the first question, so this roughly 300 globular cluster that we already have in the Milky Way, I think that they are considering all the clusters that we already know. In particular, the new globular clusters that we already have are mainly in the bulge region. So I'm sure that there are many globular clusters in the stellar halo that we didn't observe yet, and they are not considered. So these new globular clusters are mainly in the bulge. And the second question about how, if I understood correctly, the impact of the proper motion error in order to estimate the Cmax and the apogalactic distance, and also the implication of the galactic model. Well, that is a very important question, because in fact, the errors or the uncertainties in the proper motion, radial velocity, and distance are crucial in order to have the orbit parameters. That's why I construct a Monte Carlo in order to take into account the uncertainties in all those parameters. In this moment, considering that the precision of the proper motion that we have from Gaia, there is not the most important parameter that produce an uncertain orbit, is the distance. So then the distance is the worst parameters in order to have a completely different orbit. And then in fact, we have to be careful in order to construct these orbits and which are the errors of the observational parameters. That I think this is a very important, and that's why I mentioned that it's not only one orbit for each globular cluster. There is a sample or an ensemble of orbits that we can have according with the errors. And based on the galactic potential, and also there is important because the orbit is completely dependent of the galactic potential that we are assuming. And all this information that I already presented is based on a galactic potential that assumed a bar in terms of the orbital classification in the galactic, the maximum vertical excursion and the apogalactic distance. This is assuming a galactic bar potential, but also it's true that if I change the orbit, the galactic potential, probably the the apogalactic distance and the Cmax will change. But I'm not expecting to change so much, because also we did a couple of tests with a different with a different galactic potential, and the variation were not so important. So, but in fact, it's important to take into account the galactic potential of the variation of the galactic potential, because the orbital parameters completely depend on the initial condition that are the observational information and the galactic potential.
Thank you very much, and say hi to Cristina Chiappini from me.
Yes, of course.
We have a question from Miriani and several more here. in the Google Doc, but go ahead.
I have a question concerning to the metallicity gradient
Yeah.
of the Milky Way. In general, the spiral galaxies, the richest objects in metallicity are in the center of the galaxy.
Mhm.
And I don't know if I understood well, but you say that the poorest globular cluster are in the bar and in the bulge of the Milky Way. Is right?
Yeah, it's right.
So I don't understand this because the gas is different.
No, I think the richest, they are in the.
Yeah, the richest globular clusters are mainly in the inner part of the galaxy that is consistent with this radiant.
Okay,
Do you want to show again the
Yes.
metallicity?
okay, because
I also had this because I go with the
Sorry.
question with Miguel, because when you show the metallicity distribution, there
yes,
are two peaks then in the
Yes.
bulge bar, but they're basically all metal rich. And people are always talking about when they see two peaks, they just divide in metal rich and metal poor, and that's not the case. This is all metal rich, no?
okay,
Yeah. Yeah. So that means that it's metal rich because look, the purple one means that the metallicity distribution function of the bulge. This is based on the classification, right? Not all the globular clusters that are in the that are placed in the inner part of the galaxy. That's quite different. Like because if we look like, for example, this distribution here is the only, we can see the both metallicity distribution, one metal rich and one metal poor, and if we look like the metal rich are confined in 10 kiloparsec. But here we have a different components that are contributing to the metallicity distribution function. And if I consider only the globular clusters that are in the bulge according with my classification, we can have these two peaks that are, we have something that is -1, a peak in -1 that is consistent with the fast chemical enrichment in the inner part of the galaxy, but also we have something that is most metal rich. This is second peak, but the most metal rich component, the most metal rich globular clusters are in the bulge.
okay. Another question. The globular clusters that are accreted. Do you know if are accreted from the external bulge or from outside the galaxy?
Outside the galaxy, yes. This is all these clusters that I am putting here that are accreted from the external galaxies at the beginning of the history of the Milky Way. And for example, let me put again this plot where all these, for example, no, sorry, this is this plot where here all are globular clusters and are separated into different accretion events where all clusters belong to that accretion event. And this is also consistent with this Milky Way merger tree. Then all these globular clusters that are accreted belong to different accretion events. For example, 20 globular clusters belong to Gaian Enceladus, 5 globular clusters to Helmi Stream, 13 globular clusters to Kraken, 3 globular clusters Sequoia, 7 globular clusters Sagittarius.
Okay, thank you very much.
You're welcome.
Okay, and I'll follow up these questions, asking what are the masses, or are these considered minor, major, medium mergers? These trees from this tree here.
Yes, exactly. In this tree are considering the major and minor accretion events. For example, one of the major events is Gaia Enceladus, like a Helmi stream, and is a minor event. And also there are another events that are here, but it's not indicating which kind of event, and this represent the mass of the event.
I see the
Mhm.
bar. Yes. And regarding these events, can you say that possibly the major mergers towards the right of this diagram, they might have contributed to metal-rich GCs as well, or only metal poor?
No, also I think that if we see, for example, if we can see this is a Gaia Enceladus. Like, for example, if we look the Gaia Enceladus, also we can see that we have globular cluster with metal poor and also metal rich component. Also here we can have something that could be metal rich, well, compared with this metal poor, right? But also we have some globular clusters that are metal rich. And also, if we look this histogram of here, there is a small bomb that represent a couple of globular clusters that are metal rich. This is from Gaia, maybe from Gaia Enceladus.
Okay, and how do you, the metallicity, how was it determined? Was it homogeneous, these metallicities that you're showing in this plot?
Well, this is a combination of it's a compilation from the literature. This is something that we have to be careful because it's a compilation and it's not simple to have in an homogeneous way the metallicity information from all the globular clusters that we know. Mhm.
There are some questions here. Horacio, do you want me to ask yours? If you want, I can do it. Or come. Let's see.
Are there two populations of globular clusters in Andromeda too? Do you know?
I didn't hear the last part of the question. Could you please repeat the last part?
There are two populations of globular clusters in Andromeda too, or no?
I really don't know. So I expect to have a different population in the globular cluster also, but I really don't know how many components. Sorry. Mhm.
Yeah.
Just another curiosity, actually. Could we consider, instead of being accreted, all the globular cluster to be the first population formed in the cloud that could be the Milky Way after all, or no?
Well, I think it's a possibility actually, because at the end, if we at the end, if we think in the process of the galaxy formation, all the galaxy formation is like a lot of accretions since the beginning of the galaxy. And then I would say that all these very old globular cluster could be also something that was formed in the very, very, very early stage of the galaxy.
There are a few more questions. Maybe I can ask one more here that is written. Why would the intermediate metallicity stars be concentrated in the innermost regions? What does it mean for their origin?
What? Sorry, so it was like a code.
Why would the intermediate metallicity stars be concentrated in the innermost regions?
And that is because, okay. This is because at the beginning of the galaxy, according with the the collapse of the material, it was like a rapid chemical enrichment. And that's why all those stars that were concentrated in that region, the metallicity is quite bigger compared with the other. That is the reason.
And how do you determine the R min, R max from the kinematic data?
Well, that is not from the kinematic. So this that are based on the orbit integration. So then you can estimate the orbit, and then when you have to integrate at a very, very, very long time the orbit in a steady potential, and then you calculate the maximum and the minimum distance from the galactic center. But this after, like for example, 10 gigayears or 13 gigayears. This is a very, very large period. That is because you could say, well, but that doesn't make sense if the galaxy has 13 gigayears, why you are integrating an orbit like a very long time. That is because we wanted to characterize this parameter in that specific potential. And the only way that you can characterize this orbital parameter is with a very long integration.
There are a few more questions, but I'll send them to you over email. Thanks a lot.
No,
It's
thank you very much. For me, it was a pleasure to be here, and I hope soon I can visit in person.
Yeah, now that we are in the same collaboration, maybe we can arrange things in person in the future. Thanks a lot. Let's thank Liz again. Já é só se você tiver salada, deu? Eu